Hello, I would like to welcome Victor Moey, who will be presenting his talk, Introduction to Graphics Analytics. We try to get these kinds of talks to enrich the learning education of our data science programs and try to give you guys kind of a different perspective other than just the classroom feel that some of our data science programs can have. But these data science programs are designed to build your fundamental knowledge for a career in data science, and it can have an impact on your career, whether you're just trying to shore up your skills in data science, or maybe you're not so good at one little thing. We have mini boot camps for those. And also, if you're trying to do a whole career change into the data science industry, or start a career in the data science industry, we offer full stack and mentorship boot camps for those, which will take you from few to none data science skills to your first job in the industry. And after that, you also have a full data science resume and a few connections. But today we're really excited to have the introduction to analytics and graphics that Victor Moey will be presenting. Hopefully we'll kind of get a sense to how to just optimize your graphics and visuals to just make whatever you're doing, whether it's a website or a graph, anything, just a little look better and then also more accurate. Victor Moey joins us from the graphics company TigerGraph, which was actually rated the most disruptive startup of 2018 by Globe Newswire. But Victor has quite a resume of his own. He's worked as a sales engineer and consultant for a combined 12 years, and for companies such as Hewlett-Packard, UMe, and Seal Software. Currently, he's a sales engineer at TigerGraph, and Victor can provide a perspective into the exciting new industry of the tech world, that is the graphics analytics, and just kind of give us a new guide through this new kind of tech. So we at Magnimind are extremely excited to host him, and we would like to ask you now to give your full attention to Victor Moey. Thank you.
Okay, can everybody see my screen?
Yeah, we can see your screen.
Okay, cool. All right, so thank you for having me. Welcome everybody. Thank you for joining us. We hope everybody's safe and safely sheltering at home. You and your loved ones are all healthy. Everybody's busy, and we appreciate you taking the time to join us today. So I'm Victor Moey, sales engineer at TigerGraph. This meetup is my way of sharing my enthusiasm about graph with as many people as possible. And my hope is that some of this will rub off on you. Okay, so let's make a start. Okay, so what is graph analytics and why should data scientists be interested, right? Why should you care, right? Here are the top 10 technology trends according to Gartner. These are the trends that have the potential to disrupt data and disrupt the data and analytics space, right? So graph analytics is right here on the right-hand side. Okay, here's a quote straight out from Gartner again, right? Graph analysis is possibly the single most effective competitive differentiator for organizations that are pursuing data-driven decisions after the design and data capture. Okay, in that same press release, first of all, they rated graph as a trend number 5. This was like in the middle of last year. And they went on to predict 100% annual growth in graph all the way through 2022. So they describe, Gartner described graph analytics as, a set of techniques, analytic techniques that allows the exploration of relationships between entities that are of interest to you, whether those entities are users, patients, organizations, transactions, accounts, what have you. Okay, so they went on to say, what's the reason for this, right? The reason for this is the reason why graph is number 5 on the top 10 list is because graph analytics is able, gives you the ability to ask very complex questions across data that's becoming more complex, becoming bigger and bigger. And these types of questions are not always practical or even possible to answer with a SQL database, especially at scale. Okay, before we dive into, and showcase some of the use cases, let's just take a brief overview of the evolution of databases, right? So everybody knows about relational databases. You start with your OLTP schema. It's kind of rigid. There's a third, fourth normal form that you have to adhere to. But it is great for transactions, right? Very high throughput. You have your Oracle, your SQL Server. This is all great for transactions. To do any kind of like serious analytics, right? You then have to embark on a very laborious ETL process, right? It could be days, it could be weeks, right? Then you arrive at a BI solution, a star schema that you can then drill down and ask complex questions, right? The issue here is that there is a latency between transactions and analytics, right? Like I said, it could be days, it could be weeks. Because of this rigidity, there's a whole key value database revolution came about, right? The NoSQL database, AKA. This is essentially a giant 2-column table, right? You have a key, and then you have a value that is associated with a key, right? So this gives you a lot of flexibility. You can just, again, very high throughput in simple transactions. If you're tracking a click stream on a website, MongoDB, Cassandra, those are great databases to have, right? But the problem becomes, what about analytics, right? Because there's no schema, to do any kind of like queries on a NoSQL database, you then have to write a small little JavaScript program, a Java program, or what have you. More serious analytics, you then have to go out of the system again to use something like Hadoop, which is very popular, or use a data lake, and then perhaps use something like a Spark, right? Then on the right-hand side is graph databases. Okay, so you can think of graph databases just like this diagram right here, right? It's a set of pre-connected entities, vertices, and edges. So there's no joins that are needed, right? It gives you a lot of flexibility in schema. There are a lot of graph databases vendors out there, and depending on your choice, right, you can have high performance with transactions as well as high performance with deep link analytics. And we'll come to what we mean by that in a moment. Okay, so here are the use cases. We see new use cases crop out all the time, but here are some of the more common ones that we see with customers, right? Entity resolution. Entity resolution is a very popular use case with Graph. Anti-fraud and anti-money laundering is a great use case. Also, there are recommendations engine, supply chain, using Graph to generate features for machine learning, social network analysis, and so on. Okay, so what I'm going to do is, continue to, work through some of these slides, but there'll also be a few demos of the use cases that have just been previewed. So I will be, my sponsor is Tiger Graph, so I will be using that tool. So just a brief overview of Tiger Graph, right? Tiger Graph is a native parallel graph, meaning relationships between the entities are essentially stored as pointers, right? Traversing relationships in a graph is an order 1 operation, right? There's no need to do a foreign key primary key table lookups. What the native graph means is the underlying storage is a native graph storage. It is not a SQL database, it's not a NoSQL database, it's a native graph storage, right? Tiger Graph is also a distributed graph database. That means it allows you to automatically shard a large data set across a cluster of machines. And we'll have an example coming up in the next slide. It comes with very good compression technology. On average, you can expect about 50% compression, right? So for example, if you have a terabyte of CSV files, right? You will probably need like about 500 gigabytes of storage on disk. And if you want to shard that, then there'll be 500 gigabytes distributed across whatever number of machines that you choose, okay? Tiger Graph comes with an extensible set of graph algorithms library, curated, available on GitHub. What's unique about graph algorithms is that, what's unique about our graph algorithms is that they are open source, okay? Like I said, it's available on GitHub, and it's written in GSQL, which is our query language, GSQL, right? It stands for Graph SQL, right? The reason we can write these complex graph algorithms like PageRank, like cosine similarity, like Louvain, is natively in GSQL is because GSQL is Turing complete. Okay, Turing complete means you can express any business logic, however complex you want, in GSQL. Okay, it also has a multi-graph feature. Okay, what this is the ability to have store multiple graphs in your databases segregated by users. Right, a user can only see graph number 1, another user graphs can only see graph number 2. Okay, it also, so this supports multi-tenancy. It also gives you the ability to share portions of the graph with different users, right? And all this intricate permissioning is done with either RBAC, right? Role-based access control. Already talk about GSQL. Again, it's our query language. Because it's Turing complete, you can think of GSQL as a high-performance programming language for graph analytics, right? Remember I said tiger graph is a parallel graph, right? So GSQL is actually a parallel programming language. It allows you to traverse your graph, your nodes and edges in parallel, filter them, as well as do computation. It comes with this thing called Graph Studio, which is our visual SDK. It's essentially our web user interface to the back end. And I will be using Graph Studio for the demos. A major feature for Tiger Graph is the ability to do what we call deep link analytics. And deep link analytics is essentially anything above like 3 or 4 hops, right? So we have folks that are in production right now doing 11 hop queries, 20 hop queries, and we'll have an example of that coming up. Okay. So one major use of this ability to do like 10, 20 hops is to use Tiger Graph to generate features for machine learning solutions. So let's take a look at a real customer deployment. Here we have a customer with 6.6 terabytes of data, and that kind of broke down to about 20 billion vertices and 95 billion edges, right? So you can think of a vertex as the equivalent of a row in a SQL database. So 20 billion rows and 95 billion edges, meaning the equivalent of a foreign key to primary key mapping. And they were able to do this, sharded over 4 machines, each with 128 gigabytes of RAM. And using parallel loading, we were able to load up this amount of data, 6.5 terabytes of CSV files in 4.5 hours. Distributing the data across 4 machines also helps with getting better query performance, as well as better QPS. The QPS, they were able to get 2,300 queries per second with this configuration. And on average, they were doing 11 hop queries, returning in 129 milliseconds, right? Now you can think of a hop as the equivalent of doing a join, right? So 11-way table join in 129 milliseconds. Just think about that for a moment. Okay, so like I said, we'll be showing some of the use cases using Tiger Graph Cloud. The nice thing about it is it comes with this starter kits. Okay, Tiger Graph Cloud is essentially a database as a service offering from Tiger Graph, and so what's nice is you don't have to download anything or install or configure anything. You just come in and select and go. So the whole idea is to get you going faster, right? And depending on your use case, depending on what you're trying to do, you could potentially deploy in days or weeks, right? There's no need to procure hardware. Again, no need to install software, download, no need to configure your cluster or anything like that. Sign up on an account, pick the right size, and then you're ready to go. Okay, so let me show you here. Right, so you go to tgcloud.io. You can register, sign up for a free account. Okay, you sign in with Google. Once you sign in, you have your dashboard, right? It tells you how much credits you have, how much you've used, all this kind of stats. So if you sign up, right, I recommend that you can certainly share the name of your company with us if you want, but put in parentheses Magnimind Academy, right? That way they'll limit the number of sales emails that you'll get from us, right? So anyway, what I'm going to go to is the solutions, right? You can come to your solutions. My solutions is a list of all the different solutions that you've tried, right? So you can come in and say create a solution. You can select a blank slate, and here are the starter kits that I was talking about, right? So it's like 16 plus starter kits. I will actually demo some of these. Customer 360, I will show you. Entity resolution. So you come in and you just select one, right? Fraud and anti-money laundering. We currently support AWS. Coming soon will be Azure as well as Google Cloud. Now, what I typically do is I select this right here. It's $2.78. It's a very inexpensive way to explore the various use cases. However, if you want, you can also choose the free tier. The only limitation here is that you can only have one free tier per account. Okay, so I'm going to choose this here. You come in and select. You can also select all the way up to 96 virtual CPUs with 768 gigabytes memory. Select the region that you want, the disk size, the partition factor, as well as replication. Give it an initial password. Next. And then it gives you a summary and you hit submit. Okay. Now I'm not going to do that because I already have a bunch of solutions here. But essentially, once it's ready, you come in here to start the solution, stop it, terminate, right? So if you don't stop this, right, the cost keeps incurring, right? So if you're done with something, you just go ahead and stop it, right? You just come here and it opens up the solution for you. And this is Graph Studio. This is the social network, okay? So the first use case that we're going to talk about is anti-fraud, right? So let me go to the Graph Studio for this, right? So this is Graph Studio, right? It's a UI for the backend, right? It's a very nice, handy tool for you to, just point and click, drag and drop, and type a little bit. You can design a schema, create a loading job, map data to the schema, load up the data, and do like ad hoc exploration, as well as write queries, right? So this is the anti-fraud graph, right? I want to quickly show you. Here's the schema, right? So this is a label property graph, right? Think of this schema as for something like an Uber, right? A ride sharing, right? You have users refer other users, a user receive transaction, receive a transaction and transfer transaction between two users. And there's a payment instrument involved with these payment for services, and they're paid by a device token, probably a mobile device. Now, you can read data in from multiple sources. You can do CSV files, JSON. There are connectors for Kafka, Spark, JDBC, and so on, right? So if you use CSV files, right, all you have to do is to drop the CSV file, upload, and then drag and drop, say, this particular file here for the device.csv. These columns, I want them to map to these attributes. Drag and you do the same for the edges. Okay, so the edge would be, so this is for the edge from the user has tokens, right? User has tokens. So it's basically a source. The edge is essentially a source to a target, right? From the user to the device token, and the information is coming from the CSV file. So you kind of wire the whole thing up for every edge, for every vertex in your schema. This for payments and so on. So you load up the data, right? So once you're ready, you just click this little button here and it will load up. Okay, so you can see it's already loaded for you. I'm not going to load it again because it's kind of not huge, but decent size, right? So the total number of vertices is 1 billion. The total number of edges is 4 billion, right? So it's a total of 5 billion vertices and edges, right? So it broke down to about 80 million payment instruments, 80 million device tokens, 80 million users, 800 million transactions, and so on. Okay, so it's not like a huge graph, right? It's not across multiple machines sharded, but it's a decent size, 5 billion, right? So I'll come to explore graph in a moment, but I want to go to the right queries. So the right queries, this is where Graph Studio kind of functions like an IDE, if you would. Okay, so this is GSQL. Like I said, we borrow from SQL whenever possible. So you can see your select from, and you can actually put in a where clause. But on top of that, right, we have changed the syntax a little bit to kind of conform to a what we call a traversal block, right? You traverse from a source vertex on an edge. In this case, it's an OR, right? You can use aliases to a target, right? Now you can see also a while loop in here. Various print statements. You can see some type of set accumulators, data types. It's Turing complete. So what does this do, right? This query looks at transactions and to see if that transaction is actually coming from the same user, right? The receiver and the sender is the same. So how does it do that? So let's run a sample transaction 100. Okay, so you can choose different layouts. Okay, so this transaction 100 is between two users. The red ones are users, 9752 and 9753, and each users have multiple payment instruments as well as device tokens, right? So you want to see, are there anything similar, anything they have in common, right? And in this case, the answer is yes, right? These two users, although they are two separate users, they share the same payment instrument. They share two payment instruments, as well as device token, right? So this would be, a suspicious transaction, right? Potentially the same user fraud, right? Using the same mobile phone, paying back and forth between each other. Okay. Now we also have a query that I want to show. It's a classic circle detection, right? This is the classic fraud where I pay user one pays user two pays user three, and then it goes all around and comes back to me, right? That's in the fraud detection, that's called a fraud circle. All right, so let's try. All right, so for user 101, so the answer to the question for user 101, yes, that's definitely 3 circles here, right? This 101 pays 1703, then goes all around, and there's 3 of these here, right? So this guy has definitely, it's what called 3 fraud circles here. We can try another user just to show it. Okay, this guy looks more professional, right? Definitely a lot of circular relationships in here, right? So note that this circular relationship, a lot of them are multiple hops, right? Multiple hops, and the result came back like in milliseconds, right? So this is why graph is perfect for any kind of investigation, any kind of like real-time fraud detection, as you can see with a lot of the banks, but a lot of banks are doing right now. Okay. All right. So the second example I wanted to show was social graph. Okay. So once you see the status is ready, right? You start with you start the solution, right? You start the starter kit, and once it's ready, you just click on this little here. It opens up. Okay. So here is the social graph, right? The social graph is used for investigations. It can be used for anything else, right? So what it is again, a label property graph. You have a vertex type, a person, he has a full name, date of birth, email, gender, what have you. And we know everything about this person, right? It's kind of like a star schema, right? Every phone number that person has, all the phone calls that this phone number has participated in. We know all the bank accounts for that person and all the funds transferred for that person, for that bank account, for each and every one of those bank accounts. We know everything about that person, right? How many hotel stays that he or she has, how many flights, all the addresses, okay? So same thing, you just go through. I was hoping to show, okay, here we go. So you do the same thing, right? Here we're doing CSV files again. We're trying to map this CSV file called train travel records.csv for this little edge right here. What this shows here is we also have ETL functionality. Okay, you can concatenate two columns and have the output go into one of the attributes here. There are also ETL functions for converting a string to a Boolean, converting to an int, uppercasing, lowercasing, trimming white spaces, and so on. Okay, so some ETL functionality that's provided here. Okay, so same thing, you wire everything up, you load up data, and in this case, we have 23 million vertices and 43 million edges, broke down to 195,000 addresses, and you can see right here, 7.8 million funds transfer, 11.7 million phone calls, and so on. Okay. So in this case, what I want to show is showcase is this explore graph. This is used for ad hoc exploration. Okay. So let's say you're conducting an investigation of a couple of people, right? User 1005 and 282. You come here and say, person, give me the full name. Okay, so Nicholas Morris and Stephen Webb. Okay, let's say you're conducting an investigation and you know that 1005 is a bad actor. That person is, has committed some crimes before. And now you're investigating Stephen Webb. Okay, you have a hunch that the two are related, right? So what can you do, right? So I'm sure everybody has heard of shortest path algorithm, right? That's classic for fraud investigations, right? You want to see if you can connect the dots between the two of them, right? Is there anything that connects these two? So you come to find paths, okay? Shortest path algorithm is so common that we actually have this. Remember, I said Graph Studio is a Visual SDK. It's actually baked into the UI. Show one shortest path, show all shortest paths, show all paths. And shortest path algorithm, you need to tell us how deep you're willing to go. It starts with 6, right? So the way you do it is you first put the source and the target right here. You click here and you come here and you automatically populate it for you. Put your mouse here and click on the vertex and it populates the type and the primary ID for you automatically. And then you click on find path, right? So it didn't find anything at 6 hops. You find anything at 7. Let's try 9. Still nothing at 9. So we found something at 10. Let me change the layout. Okay, so you can count it out, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is 1005, and that's 282. Now, let me move this away, get a little bit larger real estate. So what do we find here, right? 1005 has a bank account transferred to another bank account, money transferred to, who then transferred to another account belonging to Cedric Weaver. Cedric Weaver has a hotel stay event with Lowell Palmer, who also went on to stay in another hotel, Highland Hotel, with our target 282, Stephen Webb, right? So there you go. Shortest path algorithm. We connected the dots, over like 3.5 billion nodes and edges in what you saw milliseconds, right? So the money trail kind of stopped here, right? So you could say, okay, I wonder if there's any more money trail going forward here. So for this, we can actually try something here called expand from vertex, right? So if you, let me go back here. Look at the schema, right? Expand from vertex means you can specify a path, a specific path to expand. By default, if you click on a vertex, it will expand all the next door one hop neighbors for you, right? If you don't want to do that, you can use the expand from vertices, right? So you can hit undo. So what I want to do is I want to get the bank account, right? Bank account for this guy, right? We have bank accounts for the ones going downstream here, but Cedric Weaver, we only have hotel stay event for him. So what I want to do is come in here and say if I click on Cedric, right, I want to expand has bank account, and I want to go to show only the bank account. Okay, so now I click on Cedric and hit expand. Okay, sorry, I already did that one. We already have that one. We want to do this guy right here. So I click on this, you see populates over here. Click on expand, and it shows just only the bank account. Right, so I want to do the same thing for Stephen Webb. Expand, and there you go. So now what we can do is utilize the shortest path algorithm to see if there's a path between this guy to this different bank accounts, right? So remember what we're trying to do here is, because the money trail kind of stopped at this guy here, right? We want to see if it continues. And to do that, I have expanded to the bank accounts. And now I can go back to our shortest path. And now, so, okay. If I want to do a shortest path, if I want to look for only money transfers, right? So I could just limit the shortest path algorithm to a certain set of vertices and edges, right? So this is the money transfer thing, right? So a person has a bank account that's part of a transfer. So a funds transfer is between two bank accounts. Okay, so I'm only interested in person, bank account, and funds transfer. And the edges that are of interest to me are has bank account and has funds transfer. So I can, before I go ahead and populate the two source and target vertices, I can come in here and say, here are the vertices, here are the paths that I want you to take, right? So what do we have? We're interested in has bank account. We're interested in has funds transfer. And for vertices, we are interested in person. We're interested in our bank account. And then funds transfers, right? So now, let's so this is the bank account I'm interested in. Is there a path? So remember, the money trail stopped here. I expand it to the bank account and want to see if there is a shortest path between this and this here, right? So again, shortest path, I'm going to just leave it at 10. And voila, there is. The highlighted is essentially saying that there is, I don't know how many this is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, right? So we would have gotten it with 9, right? But anyway, we got it with 10. So this is how it looks. This is the original subgraph that we found, and this is the new link that is highlighted that we saw, right? So we found now the money trail did not stop there; it actually continued. We can just, for grins, try the same thing with this guy. Nothing at 10. Let's try 11, and there you go. So you can see how just by using a very simple algorithm, shortest path algorithm, we can use it to explore an ad hoc exploration of anti-fraud use cases. Now, if you find yourself doing these things manually over and over again, right? One option is to, see if you can automate this whole thing, right? So we've written a query here, pretty intense. It's called discover all social connections, right? So given 2 users, 2 persons, right? Find any combination of these guys here, where these 2 people are connected, right? So pretty intense query. I'm going to run it. I'm going to do 1005. 1005 and 282. Let's go 8. And again, you saw it came back in sub-second response times, right? So this is 282 and 1005, right? So this is like your big brother use case. So Stephen Webb has a phone number that's part of a phone call. I'm just tracking one of these to another phone number belonging to Tracy Rodriguez. Tracy has a bank account transferred to another bank account belonging to Myrtle Jenkins, who then make a phone call to another phone belonging to Hazel. And Hazel has a hotel stay event with our target 1005, Nicholas. Okay, make sense? Yeah, so that's the anti-fraud use case that we're going to show. Back to the slides here. So we talked about the starter kits. If you go to tigergraph.com/starter kits, right? Every one of them, and there's a brief overview. What's nice is that there's also a video preview of the use case. So you can click on it. It will actually show you some of the things that I just showed. So again, we're adding starter kits all the time. The other ones that you can preview. Okay. Okay, so that we just did that. Here's a real use case from one of our customers. They're using TigerGraph to using deep link analytics to detect fraud in payments. Right, this particular company was in the payments industry. Sorry, here's the schema that they use. Right, an account is with a bank. It's set up by the user. A user is authenticated by the phone number. Also authentic, two-way authentication via email and phone. The account is associated with a mobile device, which is used with a phone number. Okay, and the payment is between 2 accounts. So here's a typical payment, right? Payment 1 from account 1 that's associated with device 1 with the phone number 1 and so on, authenticated with email 1, phone number 1, right? The payments is going to account number 2, which is from another bank. It's associated with user 2. So right away you can see 3 hops, right? 3 hops. But going further, we're able to ascertain, doing multiple hops, right? 3 extra hops. We are able to find that this phone number 2 has actually been is associated with a device, Samsung Galaxy S8. That's previously, going back to the history, used with an older phone number that was part of a stolen credit card transaction, right? So being able to do the extra hop, right? 1, 2, 3, 4, 5, 6. You're able to use diagraph to detect fraud in real time. Okay, so it's a real use case. Next thing I want to do is a customer 360. Okay, and this will showcase again graph exploration, deep link analysis, and then we go into the similarity algorithms, Jakarta similarity. Okay, so for this, I'm gonna, you can come to go to your cloud and start it. I already have it started. So customer 360, right? So this is Salesforce, right? So if you're familiar with Salesforce, you recognize this right away, right? So the things come into your Salesforce as leads. Leads get converted to a contact. When there's an opportunity, the contact is attached to an opportunity. Contact is also belongs to an account. Account has multiple opportunities. And then there are campaigns, the marketing campaigns. So this customer 360 is from the attribution aspect, right? Opportunity is driven by campaigns. There are multiple marketing campaigns that are pumped out by the marketing department, targeted to leads as well as to contacts. Okay. So I am going to use Explore Graph. So I'm going to hide everything. So let's start with an account. Okay. Okay, right here. Okay, VRG payments, right? So this is a Salesforce example. VRG payments is essentially a fictitious payments company. They're interested in various anti-fraud solutions using a graph database, right? All these don't exist. It's been obfuscated, right? So I'm going to use Explore Graph to show, attribution. Get more real estate here. Double click. Okay, so right away you can see everything about the account. There's the two opportunities. The opportunities are the green vertices, right? So there's one that's a renewal, 3-year agreement. There's another one that's fraud circle detection, customer 360. And this opportunity just it closed in fairly recently. You can see this account. There's multiple players that are involved, everybody from data engineers to principal software engineers, right? So it just shows that, to close deals at the enterprise level, a lot of people on the client side is involved, right? So people, from managers to SVP, CTOs, and so on. Okay, so let's say I want to see what took place. How did this opportunity close? How did it came to be signed, right? So I can use Explore Graph by just double clicking. So right away it shows me all the different, the subgraph, right? The highlighted are the subgraph, right? So I can say, show only the highlighted subgraph, right? So this is everything about this opportunity. So this is driven by that. Let me close that one. Okay. So right away, I see that there are 3 people that are involved in this opportunity. There's Sam Eisenberg, who's an architect, Joshua King, he's a data engineer, and then Jamie Walters, who's the senior manager of credit, fraud, and decision support. Now, I noticed that Sam Eisenberg was created on June 12th. The other 2 contacts were created or converted from a lead on June 21st. So if I'm gonna make a guess, I say this is the guy who made it all happen, started the ball rolling, right? So I'm gonna use the same trick, double click on Sam Eisenberg to get his view. What kind of role did he play? What kind of interactions did he have with the company to bring about this deal, right? So same trick, show only the subgraph. So this is Sam's world, Sam Eisenberg, right? So the blue vertices are basically campaign members, right? So you double click on that, it expands one more hop. It tells you what the campaign is. So for example, we know on August 6th, Sam downloaded the benchmark report. I can go on and on, right? To give me like, and then I can arrange these vertices and edges on. You can see here on 2018, July 10th, he downloaded the G-SQL white paper, and I can go on and continue. Okay, now I can do this, or if you find yourself, doing a lot of these things over and over again, you can just write a simple program, a G-SQL query to do that same thing, right? So we've written a query here called customer journey subgraph, and here's a sample inputs, Sam Eisenberg. And I'm going to hit run. So this is Sam's world. So instead of doing that manual exploration, I can just write a query and do this, right? So here are all the things that he has done, right? He downloaded a free trial. He downloaded a G-SQL white paper. He signed up for test drive. He sat in on the G-SQL webinar. He downloaded the benchmark reports. He requested a demo, and so on. Now, every one of the queries that we run, if you run it in Graph Studio, then you get the nice visualization, right? But the results are also available in JSON. Okay, so you can pump this JSON into an alternative UI. So here's one that I've done. Right, it's a simple HTML. Right, it comes in, it takes the name of the contact, and then the time frame you want to see. You want to see in a swim lane. So we go ahead. So in the background is essentially calling this query that I just ran. Okay. So here now I can visualize the journey in a swim lane fashion, right? So I know on June the 1st he signed up for the developer edition. Shortly after that, he requested a free trial, had a sales meeting. He downloaded a G-SQL white paper. No, sorry, he sat in on a webinar. It must have been very impactful because he went on to download the G-SQL white paper. He sat in on another anti-money laundering webinar. Remember, this is a fictitious company looking for AML solutions. Downloaded benchmarks, requested a demo, and so on. Okay, so next I want to talk about similarity algorithms, right? So let's say you're analyzing Sam Eisenberg's journey, right? And you say, oh gosh, this is a pretty ideal, right? I wonder if there's a way to find out how many other Sam Eisenbergs are there, how many other people out there, prospects, that are like similar journey as Sam Eisenberg. Okay. So this is where Jacquard similarity comes in, right? So we've written a query here called similar customers. It takes campaign types, it takes the contact, and based on relationships to all the webinars that Sam has participated in, all the demo sign up and trials that he has signed up for. I want to see all the prospective customers out there that are on the similar journey, right? So you can pick any of these here, right? So webinars and demo sign up and trial. I want to see how many people out there share the same journey as sign up for the, it's the same, downloaded, ask for the same free trial, downloaded the same white papers, and so on. So we can do that. Say Sam Eisenberg. And the sample data is, the sample inputs are just right here. So you copy and paste. And let's say I want the top 8, right? You can do whatever you want. In this case, the results are not so interesting in a graph format, right? Because you just want the bare bones data. So you can just go to the JSON. And here we've calculated something called similarity, Jaccard similarity. And then we've actually put it in descending, ascending order here. Okay, so before we talk some more about this, let's just briefly review Jaccard similarity. Okay, so Jaccard similarity essentially says, find similarity between 2 sets, right? You have 2 users, right? Sam Eisenberg and Priyanka Patel, right? 2 sets, and you can calculate the Jaccard similarity by, in this case, set A is Sam Eisenberg, set B is Priyanka Patel. Oh, sorry. The formula is like this, right? If you know the cardinality of the intersection size and the cardinality of set A and plus the cardinality of B, you can essentially calculate the similarity index. Okay, so how would this look like in a graph? This looks exactly like this, right? So Sam Eisenberg has participated in a free trial, developer edition, and all these things, and Priyanka has done the following. You can do this in a graph like this, right? So Sam Eisenberg has attended, signed up for a free trial, downloaded the developer edition, signed up for a free test drive account, attended the AML webinar, downloaded the benchmark report. Priyanka has only done 3 of those. Now, how would you compute the cardinality of A? In G-SQL, there's a function called outDegree. You apply the outDegree to a vertex type, and it will tell you how many outdegrees are there. So outDegree for Sam Eisenberg in this case would be 5. 1, 2, 3, 4, 5. Likewise, outDegree for Priyanka Patel would be 3. So we know the cardinality of set A and cardinality of set B. How about the intersection size? To do the intersection, you just do the traversal, right? So you traverse all these from Sam Eisenberg, you traverse out like this, right? And then you traverse from the campaign to Priyanka Patel or anybody else. Every time you traverse to a target customer, you add 1 to a counter, okay? Traverse the second time, you add another 1, it becomes 2, you traverse this, it becomes 3. So just doing the traversals and doing computations in G-SQL, you can compute the size of the intersection size, the intersection set, okay? That's essentially what this is. Jaccard similarity. You can see here, this is how it's computed, right? The intersection size multiplied by 1.0 to make it a float. Set of the set size A plus size of B plus the intersection size. The intersection size is computed above. Okay. So what we did was we ordered by the similarity in descending order, and we limited it to the top K, which is this guy right here. Okay, so this is top 8. So we ran 8. So you should get 8 of these guys in descending order, right? So Priyanka Patel has a similarity index of 0.3. Scott Tate has 0.25. Helen Fisher is 0.25. Vincent Chen is 0.25, and so on. So I've actually showed it in a graph, right, separately, and I copied the image for you, so you can see it right here. So Priyanka has on this here are the campaigns that Steve Eisenberg has participated in. You can see that Priyanka Patel has 4 things in common with Steve. Sam Eisenberg. Right? I can see the 4 edges going out. That's why she's got a 0.3. Vincent Chan has only 3. Okay, there's only 3. That's why he's a lot less. And same with Scott Tate. We're just showing a sample here. Okay. So what could you do with this, right? So by finding similar customers on the customers that are, prospects that are potentially on a similar journey, you can then use that as the basis to, recommend next best action for this person, right? The next best campaign the next best webinar that we think you should participate in, you offer that to that person in an email. Okay, so you can automate this whole thing. This is our version of Customer 360. Okay. So the next, so before I go there, right? You will see in a similar customers query, the results you can see chronological order goes down to 0.3, 0.23, 0.2, 0.2, and then 0.18. Okay. Now notice that this is Salesforce data, right? People sign up for things using fictitious names, right? So you really don't know who this is. This is kind of frustrating for a digital marketing person, right? They want to send an email, then the email will start with "Dear?" right? That's not ideal, right? So the problem is there a way to find out who this person really is, right? This problem is called entity resolution. It's possible, okay? And that's the topic of our next use case. Okay, entity resolution. Okay, so what is the problem? The problem really is one of duplication, right? So if so to resolve the entities, right? So why would you want to do that, right? You want to do that to have a complete picture of your users, your customers, patients, what have you. So you can track and record that person's journey on your website. If you cannot do that, then it hampers your ability to recommend the right things to them at the right time if you don't know who they are. So the problem is duplication, really, right? So you have, in this case, a single real-world entity that's represented or recorded as several digital entities, right? Anybody who has multiple Gmail accounts know what I mean, right? Victor Moey at gmail.com, vmoy@gmail.com. Are these the two people the same, one and the same person, right? Another example would be Zillow, right? So I could be logged in on my laptop on Zillow.com with my personal email address. Zillow knows who I am, as I'm browsing for properties and whatnot. Zillow will know, my history, what's my preference, right? But I will also go home and on my mobile iPad, I would also go visit Zillow.com anonymously, not logged in, right? If Zillow can somehow connect the dots between these two separate website visits, then they'll have a more complete picture of my history, just using these two devices, right? So the whole problem of trying to connect these two website visits, that's called entity resolution. And we see this is a big use case with Graph across different industries, right? From airlines to media companies, to advertising companies, and so on. And sometimes it's just people using different names, right? So for example, you might have Paulo Rodriguez, right? He came, immigrant from Mexico 20 years ago. After spending 20 years in the US, he likes the country. He now goes by Paul, right? If there's a way to connect the two together, these two are the same person, right? Then you have a stronger hand in being able to recommend things to him, right? And sometimes duplication happens just because just honest mistake, right? A typo, right? Scott Parshall from Pittsburgh misspelled, and Scott Parshall from Pittsburgh spelled correctly. This unfortunately ends up as 2 records, and it's up to the task of entity resolution to resolve it. Okay. Here's the example I was talking about. Zillow.com, right? If there's a way to map, anonymous users to actual registered users. You have a more complete picture of the history, of the browsing history and whatnot, search, and you will be better able to recommend properties that are of interest to this person. Another use case, state county government, right? They want to, they're getting their hands are full from trying to see, different identities, different people applying for different benefits, EBT cards, and so on. And each family could be double dipping and so on. So that's a really a big problem, right? So the case management system for this county government is a very old, 25 years, different technologies coming from different vendors, right? So you have data from different sources, right? And that could be 1,000 Joe Smiths, each with different phone numbers, different addresses. Some of them are the same addresses, but slightly different names. Are they the same family? Trying to find out who's who became a real challenge, right? And especially, with families that are on welfare, sometimes across generations, that could be mother, father, and son, all triple dipping onto the system, right? So that's the problem at hand. Yeah. So they tried to solve this with using Tiger Graph to come up with a master data management system to save both time and money with most, and to be able to connect the dots instead of having them siloed in a relational database. Multiple approaches to resolve entities, right? That's the deterministic approach, and then there's the probabilistic approach, right? The deterministic approach is, you have very clear, specific information that's, a PII information, right? So you can have two entities that have the same social security number, they could have the same birth date. Those are pretty good, right? Name and birth date are pretty good, but it's not foolproof if you have a large data set. And you need to be aware of typos, essentially. Sometimes typos are intentional, sometimes it's unintentional. A second approach is probabilistic, right? With the probabilistic approach, right, you realize that you're not going to get perfect matches all the time, and for whatever reason, right? So maybe you could say a perfect match would be 100, an imperfect match would be 80. Now the question is 80 good enough, right? So this approach, you could go like rules-based, right? So you can, okay, every time there's a match on the last name, okay, that's worth 20 points. That's a match on the birthday, okay, that's a lot stronger match, right? Maybe you give it 30 points. That's a match on the, the residential address matches. That's pretty good too, right? So you then give these, every time there's a match, you give it a score. You accumulate the entire score, and then if that score, and the total score exceeds a certain threshold, you could say, okay, we got an 80 score total, all right? So your 80% chance that these two entities that you're trying to match are the same. Okay. So so another use case would be, so let's talk about the first use case, the deterministic approach, right? Here you have multiple data sources, right? Each data source has a piece of the puzzle is not complete, and then it's up to you to match and merge these different pieces together to kind of, it's kind of like a jigsaw puzzle, right? You have data source number 1, number 2, number 3, number 4. You bring it all together, merge it into a graph database to get a complete picture of who this person is. And then you link this merged entity back to the data sources. Okay, so that's a deterministic approach. In a probabilistic approach, like I said, right, in a graph, using a graph, right, so you have Paul Rodriguez and Paulo Rodriguez, right? They both share the same last name. So that's a person, and there's a last name node. It's also attached to a phone number. It's also attached to email, address, and so on. All these are called attributes, different colors. The blues are the people, person vertices. So every time there's a match, right, you give it some points. And how do you know that's a match, right? You traverse from here to here, and from here back to there. So that's a match. These two persons that you're trying to resolve, and it could be the same person, They share the same phone number. They share the same last name. However, the email addresses are different. So what would you do? There's no match on email, but there are matches on that. So like I said, right, you give it a value every time there's a match, and then you accumulate that, right? And then if the total exceeds a certain threshold, you can say, okay, create an edge between the two of them to say, okay, these two are probably the same person, and you can even put that score in there. It's 80% chance that they're the same, 90% chance they're the same, right? So the address is different, and the email addresses are different, right? So what could be the case here? To notice here, this is probably the personal email address. This looks like a work address. So this could be the physical address of the work for Paulo, and this is the residential address for Paul. Okay, and whether or not they're the same, it depends on all the attributes that you have matched. A second example, right? Same thing, Paulo Rodriguez and Paul. This time they share the same address. So it looks like it could be the same person. Very, very likely the same person. However, the passport numbers are different. So what kind of industry where passport is of interest? Airlines, right? So if you know, the airline sees Paul Rodriguez flying, you know, at T1, and then Paulo Rodriguez at T2, you know, these are two different entities as far as the airline is concerned. If there's a way to match them, right, and say, okay, these are the same person, then you can have a more complete picture of this person. You can merge the two, flight history, preferences, and whatnot, and better be able to recommend things to them, right? So how do you explain the different passport, right? How about dual citizenship, right? Maybe Paulo was a Brazilian immigrant, and in this country, it's very common to have dual citizenship. So after some time of immigration to a certain country, he becomes Paul Rodriguez, right? And a different passport number. That could be one explanation. So if you can merge the two of them, even with these two different passport numbers, then you have a more complete picture of who this person is, right? He could be a, you know, at work, he could be an executive, right? And he could be flying for leisure as his personal in using his other passport. Okay. So solving entity resolution problem, right? So this is, like I said, right? It's a matter of matching the records, and then once there's matches, if there's enough matches, you want to link them together. Okay. And once you've resolved this in the graph, then you can go on to do, you know, business intelligence on this connected component. Okay. You can go on to do, you know, real-time recommendations. You can do similarity, a whole host of other things that you can do. Okay, so record matching and linking, right? So you have two records, you have two vertices, right? And you want to link them if they have similar user profiles, such as, you know, same first name, same last name, date of birth. You can also see if, you know, they're logged in, you know, are they using the same IP address, right? Are they using the same device, the same phone number? Do they have the same cookie, right? And you can also explore relationships as well. Do they have the same home address, work address, even geospatial? Do they, you know, attend the same school? Do they have the same employer? All these will allow you to, you know, probabilistically decide if it's a match or not. So it looks like this, right? You have your records, you use it, you come up with a schema, and you populate that schema in a graph, and then you run your matching algorithm. And depending on the outcome of the matching algorithm, you either link or not. So that's rules-based, right? I'm going to show a demo of entity resolution using rules-based approach. You can also use, you know, similarity-based algorithm, and you could use things like cosine similarity, you know, with weights. Okay. And then the linking part, right? So once you ascertain that you've determined that two users are one and the same, right? You have multiple choices. One is to link them, right? This user is the same as this user, who's the same as that user. Another approach is to create yet a brand new vertex called a universal ID, right? And this universal ID is all these entities are the same and they are represented by this universal ID. What's nice about this approach is that you have all the context preserved, right? So Paulo Rodriguez, Paul Rodriguez, everything is preserved, where it came from, right? Another approach, of course, is to merge. Now, if you merge two records, then you lose that context, right? Paul Rodriguez is actually a vegetarian. You don't know if it's really Paul who's the whether it came from Paul or whether it came from Paulo, right? That has been lost if you merge. Okay, so the demo I will show, we will be doing linking. And then, again, once it's resolved, you can continue to do, graph analytics. Yeah, you could do better delivery of advertisements, right? Both Paul and Paulo, they seem that according to their browsing behavior, they've clicked on Tesla ads before, right? So you could sell that impression to maybe would-be advertisers like BMW. Right? You can recommend things with a higher conversion rate, right? Do customer 360 like I've just shown. Okay, so I'm going to go back to the cloud. So I've shown the social graph, right? So once you're done, you typically want to stop this because it costs money. So entity resolution, I'm going to open up, I'm going to log in, quit out of this. So here's the schema, right? So this is like a fictitious video streaming business, right? So people sign up for an account. That account has an IP address. We track the IP address. We know the email, the last name, the phone number, the address, the device. And this account, has video play events with, they stream different videos from different genres, has different keywords in them. Okay. So I'm not going to go through this, no data. Okay, so I'm going to show, sorry. There's the same owner relationship. Once we determine that two accounts are the same, we link them together with the same owner edge, right? So I've got 900 of these guys. So actually I want to clear out delete the database, clear the graph, and start fresh. Should have done this earlier, but anyway, bear with me. While I do that, I'll open up another tab. No running away from it. Yeah, so what I just did here is to basically clear out the graph, right? Basically delete all the edges, delete all the vertices. And okay, so it's cleared out. Everything is zeroed out, right? So I'm going to go ahead and repopulate. And I just want to show you, want to start from a clean slate, right? So in particular, when it starts out, when we populate a database, none of the owners are this. We have not matched at all. So there should be 0 same owner edges, right? So as you can see, it says it's finished loading this CSV file. It's finished loading that. That one is pending. And now we just need these two to finish. Okay, good. It's done. So same owner. You can see same owner right now. We've not done any matching. We've not done any links. Okay. So let's go over to write queries. I'm going to show the query for account matching. So every one of these starter kits, like I said, right, comes with schema. It comes with sample data that's already loaded for you. Actually, it's not loaded. You have to load it yourself. You have to come in here and click that. And it comes with pre-built queries, right? So here's the matching algorithm. I'm going to go back to design query here. Okay, so this is what we're trying to match, right? So an account, the accounts come in, an account has an IP address, has a last name and all that. What we're trying to do is here's the G-SQL algorithm. I think it's pretty elegant how it's defined, right? So what we're doing is we're saying from the input account, right? And we have a threshold, right? Threshold is that if it exceeds this threshold, we're gonna link it. Okay. So we select from starting from the account. We want to traverse the has IP relationship, the has email, has all the hashes, right, to a target. From here, we're traversing to all these attributes. That's what this variable has now, right? So this variable contains all the IP address, the last name nodes, the address, the phone number for this particular account that has been input. Okay, and then select T from attributes, right? Starting from these attributes, we're going to go back. We're going to traverse the same edge in reverse, right? So we're going out here, and then we're going back, right? We're going to say, for this phone number, give me all the other accounts that has the same phone number. For this last name, give me all the other accounts that has the same last name. For all the emails, give me all the other accounts, right? So it's a 2-hop query, going out and then going back in. Okay. Now going back in, we're no longer interested in the input account, right? So we're only interested in other accounts that are not the input account. And whenever there's a match, right, you can see a case statement here. Whenever there's a match, if there's a match for an IP, right? If these 2 users use the same IP address, we're going to give it a 0.2. If these two accounts have the same email address, we're going to give it a 0.3. This is a plus equal, so we are adding to it. It's cumulative, right? If it's share the same phone number, 0.2, same address, 0.1, and all that. Now, so a perfect match, right? A match, 2 accounts that has the same IP, the same email, the same last name, the same everything the same. You can calculate it, right? A perfect match will be 0.2, 0.3. It's 1.3, right? So that's 1, right? So 1.3 will be a perfect match, right? So depending on the threshold, right? If the score is greater than the threshold, right? Then we do an insert. We insert the same owner edge from the input, and then we actually put the score in there. Okay, so let's give it a shot. So some sample input parameters. So let's go ahead and link 407, and we give it a threshold of 0.6, right? So what it's saying is, if we add everything up together, right, all the matches, if the threshold, if it exceeds the threshold, right, of 6 is like 0.71, 0.65, what have you, then we're gonna ascertain that these two accounts are the same owner. Okay. Okay, so now we're done. I'm going to go back to the load data. It has 2. Okay, so let's go to explore graph. Sorry. Go to explore graph. Count 407. Okay, so we have the IP address, and these are the 2 matches, right? Same owner. So what I'm going to do, I'm not really interested in all these video play events. So let me go to our expand. Sorry, expand vertices. So I'm going to say expand everything except the has genre, has keyword, play video, has play event. Not interested in that. Video games. expand. So this time I'm only expanding only the attributes, right? Okay, so 407 has this phone number, has this email address. So I'm going to do the same. Click on this guy and expand, right? So I'm going to expand everything. And this is why we got the match. Same thing. Click on this guy. These are perfect matches, right? So if you look at the same owner, right, you can see the score is 1.3. It's a perfect match. And same with 707 is perfect match. Now we can do the rest of the matching. So this is the thing that we use for matching. You can actually call this function from another G-SQL. So we can create a main query. And from there, we call it count matching with a particular threshold. So this will match everything. And now if you come back to Explore Graph, see right away that there are a lot of every one of these guys are. If there's a match, okay. So that's the entity resolution use case. So go back to the slides. Okay, so just to kind of conclude, right? G-SQL, it's a modern graph query language. We actually incorporated the best features from SQL, from other graph query languages like Gremlin and Cypher. As you can see, there's the select statement in there. It borrows heavily from SQL. Queries are composable, right? You can call other queries from within the G-SQL query. It's Turing complete. Built-in semantics for parallel execution, right? It automatically executes. Remember, I say TigerGraph is a native parallel graph. It uses an MPP engine underneath. Accumulator variables, as you have seen, allows for very fast map reduce like aggregation. The graph algorithm library. These are all a set of curated algorithms on GitHub, available on GitHub. I can actually go there to show you. Okay, so you go under G-SQL graph algorithms. You'll see a set of algorithms that are curated, and it's categorized under things like centrality. You saw similarity, or essentially what we did earlier was to look at one of these Jakarta similarity example, and which was just so it's expressed natively, right? So you can come in, copy and paste. You can tweak it. You can contribute back to GitHub. There's also cosine similarity, centrality. So if you look at page rank, right? Page rank is pretty intense algorithm. Here's page rank defined in G-SQL. In less than 30 lines, it's about 30 lines of code. Okay, so G-SQL is a language that you can use to traverse, filter your graph, and then do computations as well in parallel. Okay, so there are other algorithms as well. Classification, this community detection, right? Label propagation. If you want to do your own shortest path, it's under path. Cycle detection. shortest path algorithm, without weights, with weights, and so on. All right. Now we already went through this. You can see the different, path related. What's the shortest path between two nodes? Centrality. Which nodes are the most centrally located? Community detection is their natural grouping of vertices around these hubs. Similarity, we talk about them, and then we actually have KNN, nearest neighbor, for classification. Lastly, we'll talk quickly about machine learning. Okay, how you can use graph generated features for machine learning. Right? So this real customer, China Mobile, there was a lot of problems with people buying SIM chips, SIM cards, and then using it to do scams, right? A lot of high profile cases where, old grandmothers were cheated out of their college savings for their kids or grandchildren. And unfortunately, they took their lives, right? So then as a result, China Mobile got a bad name because people were committing fraud using, their SIM cards. So the challenge is to report scam phone calls, right? Across like 50 million subscribers and billions of calls per week, right? They needed a solution that can scale to 2,000 calls per second to detect fraud in real time. Okay. So what they did with Graph is they use for Telegraph to generate features for supervised learning, essentially, right? So there are these example features of a good phone and example features of a bad phone, right? So above and beyond things like a bad phone doesn't have very much callback, people calling you back. Okay, there's a sign that it could be a bad phone. But above and beyond that, right? They went and developed features like this, right? So a good phone typically, you would call a stable group of people on a regular basis, right? You call your mom, your significant other, your best friend, fairly regularly, right? There's a stable group of phone numbers that you call. A phone that's purchased, a SIM card that's purchased just for scamming, typically does not have a stable group of people that they call to on a regular basis. Okay, a good phone, you would have a pattern like in-group connections, right? You call your best friend calls your second best friend, who calls your third best friend, and they all call each other, right? So this is called in-group connections, right? This is another feature. Okay, is there a three-step friend relation, right? You call this person, and then person calls the number 3, right? So these are just three on the bad phone side of things, right? In-group connections are absent. Three-step friend relationship also absent. This is just a sample of 3 of these guys. Okay. So using traditional prediction history features, right? Just based on percent of one directional calls, number of rejected calls, right? You call somebody, they just hang up right away because they know you're trying to scam them. Just based on this, right? The algorithm can come back and say, this could be a fraudster, and this guy could be a fraudster as well, because the rejection rate is pretty high for these two. And these guys are probably a regular customer, Sarah, because the rejection call rate is very low. And the number of one-way calls with nobody calling back is very, very low. For these two are very high, right? So just based on this, you can say, this could be a fraudster, this could be a fraudster, this could also be a fraudster, right? Using machine learning with deep link analytics to generate these graph features, right? Things like stable group, in-group connections, three-step friend, right? You can say, okay, this one is a fraudster, right? But however, Tim does have a stable group of friends that he calls to on a regular basis. So probably not a fraudster, he's likely a prankster, right? And this one, Sarah has a stable group of people that she calls into, a lot of in-group connections. This is correctly flagged as a regular customer. Fred, on the other hand, has absent, no stable group, no in-group connections. So it's likely a fraudster, right? And then interesting enough, John, because he has a lot of in-group connections, the three-step friend relations, likely a salesperson, right? probably not a fraudster because of these two, and likely a salesperson, right? So you can see more accuracy with predicting things based on graph features, generated graph features for machine learning. So what China Mobile did was they created, using graph, they created 118 of these features, basically queries, GSQL queries that multiple hops, very deep links, some of them, and based on this, they use it to generate these features, training data to power the machine learning solution, which is one of the Python algorithms. Right. So the upside of this is that using graph to generate the training data, the features, the quality of the data, as you can imagine, is very high, right? So with machine learning, it's not about volume, right? I mean, a lot of stuff that the machine learning algorithm has already seen is not going to move the meter, right? Interesting stuff that it has not seen before, that will help, right? So with this solution, they were able to cut down on the false positive rate dramatically, thereby increasing the accuracy of their prediction that some call is a scam, some calls are not. Okay. Okay, then we have this this idea of explainable AI, right? So one of the issues with AI adoption sometimes is that we don't know how the AI system, the machine learning system, came up with a particular decision, right? It's A. Why is it A? We really don't know, right? Now you will not have this with graph, right? Machine learning using graph with very, very specific pattern, right? You can always explain it, right? This guy is a fraudster because he doesn't have any stable group. He does not, have any three-way connections, right? You can explain the decision, right? So that's what this is about. As you saw, right, we have algorithms in GSQL for PageRank, community detection, and the similarity algorithms, right? These are what we call in-database machine learning with Tiger Graph. Okay, so you can do this natively within the database without having to go anywhere else, right? You can do Tiger Graph is also ACID compliant, right? So you can do analytics on transactions as they're streaming in, as you saw in the China Mobile use case, right? It's a database of phone calls, right? Every phone call comes in, it updates the database, and the database runs analytics to say, okay, this phone call is coming from a number that's should be okay. It's coming from a number that's a scam, so on. Okay, I've come to the end here. Couple of things you can do, right? You can, like I said, go to tgcloud.io, sign up, and you can very inexpensively pursue some of these use cases that we talk about, right? You can also download the developer edition if you want. Try the enterprise free trial. That's a 30-day license. The developer is free for use, but with some limitations. Tiger Graph Cloud also has a free tier, right? You're only limited to one free tier at a time per account, but it's a good way to learn Tiger Graph for free. Okay, there's also an ebook that you can download for native parallel graphs. Additional resources. There's a test drive. That's the Graph Guru. We have a set of Graph Guru webinars that are excellent if you want to get deeper into this. There is a GSQL 101 YouTube video that you can watch. There's a certification. There's a GSQL certification that you can do. And here's the location for the graph algorithms on GitHub. That's all I have. Thank you very much for your attention.
All right, great. Did we get to any of the questions or all the questions?
How do I get to the questions?
There's a Q&A button at the bottom of your screen, right next to the share screen button.
Okay.
Or I could just read them to you actually.
I see it, but I don't see any questions in there.
Oh, really? Well, I have about 7.
Okay.
But I think you might have answered some of these already.
So how do I see this? Speaker notes? Oh, sorry. I'm
Do
sorry.
you see the share screen button?
Stop share?
You can, well, yeah, and then right next to it is the Q&A button.
Oh, yeah, that's right. I see it.
Yeah. That's where going to be like pretty much all the questions. There's looks like 8 now.
Okay. Yeah, sure. Isolation level, right? We support repeatable reads. Repeatable reads, right? So anytime so basically what that's saying is that if you inside of a query, you do the exact same select statement twice at T1 and T2, you'll get the exact same results back. The only thing might be different is if you do some updates, then the updates, of course, will be there. Is there any way to get data into Tiger Graph besides the comma separated value CSV file? Yes. So we also support JSON. We have a Spark connector. We have a Kafka connector, so you can stream transaction data coming into the platform and then analyze it in real time. Other than fraud with link type relations, are there totally different use cases? Other than fraud with link type relations, this is coming from Rakesh Sharma. Are there totally different use cases? I'm not sure. I understand that actually. We'll come back to this. I'll leave my email address with Magnimind, so in case you want to get in touch with me. Is this my first name, last name @tigergraph.com. Any examples where 6.6 terabyte was loaded into TigerGraph on 4 machines with 128 GB? This is coming from Dave. With 128 GB of memory each, did the graph data fit into the memory of the 4 machines, or was the disk on the 4 machines used? Okay, so both. Okay, so the data has to be stored. It's stored on disk. When the system is up, it will read a good chunk of that into memory. Okay, so that's how you get the zippy fast. But if it's not in memory and if it needs to bring it in memory, it will do so. Okay. Question from Richard Liu. With GSQL and some BI-like functionality on TigerGraph's product, are some of TigerGraph customers using the platform instead of Snowflake to run their analytics? We seldom run into Snowflake, right? So we are a graph database. Yeah, sure. You can do traditional BI analytics with a graph database, but we're not under any illusions that we're going to go out there and replace the Oracles, the Power BIs of the world, right? So people come to us specifically for graph analytics, like the sort of things I talk about, page rank, people do entity resolution. Hopefully, the solution I showed, it looks very intuitive, right? Sure, you can do entity resolution in a SQL database. Yeah, sure. But if you have a graph problem, right? If you want to do real-time recommendations engine using graph, then perhaps using Vertica or using Snowflake is not ideal for you because Snowflake does not do graph analytics. Question from Jael. I see TigerGraph can detect duplicate data. Is it possible to update the source system such as Salesforce to fix the entity duplicate issue through TigerGraph? I'm going to say the answer to that is yes. Actually, that's one of the projects I'm interested to show. You resolve the entities from. This is actually a use case that we got from a customer straight out, right? Because I've worked with systems that use Salesforce and all kinds of crazy stuff. It's in Salesforce. The answer is yes, right? So you just need to create an extra field in your account record in Salesforce or your lead record in Salesforce to kind of link things together, right? I've never done it myself, but I would imagine it can be done. Question from Dave, is all the TigerGraph open source or just GSQL graph algorithms? TigerGraph is not open source. Only the GSQL graph algorithms are open source. And again, the reason why it's open source is because it's Turing complete. We have no problems showing you how you write PageRank in GSQL. No problem showing you how you can do that in Java. This is very different from some other vendors out there. They would have PageRank, they support similarities, cosine similarity, but they all do that through a black box library, the Java library, right? The problem with that is if you have something, if your subgraph doesn't quite fit that cosine similarity input, then you have to kind of pre-process and move that graph into something that the algorithm needs, right? That means, taking the data out, pre-processing, and then putting it back in. It's sure as hell not going to be real time. Anonymous attendee, how does Tigraph compare to Amazon Neptune? Why don't you reach out to me directly and then we can answer that? I think it's going to be, but I'll just give a hint right here. Amazon Neptune does not compress data, right? I talk about compression. Tigraph, you have 1 terabyte of CSV file, we can compress it down. You'll need only 500 GB. In the case of Neptune, they do the opposite of compression, actually, right? So, which is ironic because, Amazon charges you for that too. Question from Randa Thompson, cost. I'm a sales engineer, I'm not in sales, so I can't really give you anything, but essentially the cost is based on the amount of RAM that's used. We don't care how many servers that you distribute that, if you need like 512 GB of RAM, we don't care if you have it on 1 machine or 5 machines or whatever. The pricing is based on the RAM. Okay.
All right, great. Thank you, Victor.
Yeah.
And thank you for all for attending the talk. It was a great in-depth look at graphics analytics and also all of what Tigercraft offers. Magnimind hopes to hold these talks in order to keep giving people who are trying to get into data science or already in data science an opportunity to just further their learning. And that's what all of you have done here today. So thank you for that. We also hope that you'll join us on April 7th, which is tomorrow, for our talk, Deep Learning 101, Artificial Intelligence Based on the Brain with Tyler Seward. Thank you and have a good evening.